Okay, so we've got a past paper question on transition metals. Specifically, this is a transition metals redox titration past paper question. It's one of the standard ones where we're going to use a thiosulfate titration to determine the concentration of copper and then work out the percentage of copper in an alloy. Okay, so we're given quite a lengthy sort of procedure that a student has undertaken. Take your time to read that. It's a 6-mark question, so there's plenty in there to digest, and see if you can pick out the relevant details. So you might want to highlight the different reactants that are taking place. I've just cut out different chunks of the question and got right to it. One of the things which is quite tricky is knowing what's relevant and what's not. So for example, the nitric acid, it does not appear in any of the balanced equations. It's just used as a reagent to convert the copper atoms in the alloy into copper 2+ ions. The sodium thiosulfate, the Na2S2O3, it's just the thiosulfate ions that we're interested in. And you'll also notice that the potassium and potassium iodide doesn't appear in the balanced equations. So it's really important to be comfortable with ionic equations, and it's a skill in itself being able to pick out what the relevant or most important species are. It goes without saying that knowing units associated with concentration, being able to convert from milligrams to grams, knowing the units of volume are also very important. I also like to start off by drawing a diagram. You might not get a chance to do a full diagram in the exam, but it certainly helps to picture while you're learning what the reagents are and when. So my first advice would be, if you could, maybe draw a diagram and also be familiar with the apparatus that you would use to carry out this type of analysis. It didn't say in the question that it was a titration, but it is obviously a redox titration. Okay, so here is my diagrammatical representation of this analysis. At the top right there, we can see that I've converted the mass of the alloy, which I've called A, into grams. So I've converted that to grams by dividing by 1,000. So the mass of the alloy A, I've given that in grams. The acid, the nitric acid, is used to convert that into copper 2+ ions. So if we go to the bottom left hand side of the diagram, all of the copper atoms that were in the alloy have been converted to copper 2+ ions, and then they're made up to exactly 250 centimeters cubed in a volumetric flask. 1/10 of those ions, or 1/10 of that solution, is then added to a conical flask, so 25 centimeters cubed of the 250 centimeters cubed goes into a conical flask. There are two reactions occurring. The first stage, as we see there, is that we add iodide ions to the copper 2+ ions, and this makes all the copper 2+ and iodide react to form iodine and copper 1 iodide. So now there is only iodine and copper iodide in the conical flask. In the second stage, thiosulfate ions are added from the burette, which then react with the iodine in the conical flask, and we can test for the presence of iodine by adding starch. Starch will turn blue in the presence of iodine, so when all of the iodine has been used up, we will see a colour change from blue, dark blue, almost black, to colourless. So from the amount of thiosulfate that is added, if we divide that by 2, that is the amount of iodine that was present, and that's the same iodine that was present at the end of the first reaction. So if we multiply that by 2, that is equal to the amount of copper 2 ions that were present at the beginning of the reaction. So divide the thiosulfate by 2 to get iodine, times the iodine by 2 to get the amount of copper 2+ ions. If we work out the amount of thiosulfate present from the burette, we can then use that to work out the amount of copper 2+ ions that are present at the beginning of the reaction. So we've got a volume and a concentration of thiosulfate, so we can work out the amount of thiosulfate. We can then use the two balance equations to work out the amount of copper ions, but remember that that's the amount of copper ions in the conical flask. We can then multiply that up to find out the amount of copper ions that were present in the volumetric flask at the beginning of the reaction. So to find the amount of thiosulfate, it is concentration times by volume. And that works out at 9 times 10 to the minus 3 multiplied by 0.08, which gives me 7.20 times 10 to the minus 4 moles of thiosulfate. That is equivalent to the amount of copper 2+ ions that were present in the conical flask at the beginning of the reaction. Because the amount of copper sulfate ions in the conical flask, well, it's 25 centimeters cubed, and we started off with 250 centimeters cubed, we can find out the amount of copper 2+ ions in the original volumetric flask by multiplying by 10. Now it's worthwhile remembering that the amount of copper ions is equivalent to the amount of copper atoms that were originally present in the alloy. So we can work out the amount of copper atoms in the alloy. We can then use that to work out the mass of copper in the alloy, and then we can work out the percentage of copper in the alloy. The amount of copper atoms in the alloy is equivalent to the amount of copper ions in the original solution. The mass of the copper atoms can be given by mass is equal to number of moles times by molar mass, and the percentage of copper is the mass of copper divided by the mass of the alloy times by 100. The molar mass of copper is 63.5 grams per mole, and that gives me a mass of 0.4572 grams. Dividing the 0.4572 grams of copper by the 0.985 grams of the alloy multiplied by 100 gives us a percentage of copper in the alloy of 46.4%. Now the question did ask us to give our answer to the appropriate number of significant figures, and all of the variables in the question were 3 significant figures at the minimum. So you have to use the minimum number of significant figures of the variables in the question, and that will be the appropriate number of significant figures to use for your final answer.